All right, yeah, thank you. And as you can see from the logos, the left one, that's us, the right one, that's the hit lab. I was so lucky to do the final work on this paper while Rob had me as a guest for my sabbatical, so thank you again, Rob, for that one. We did this work together with the University of Bielefeld, which we are close collaborating, and maybe to give you some of the ideas, we've done some photorealistic avatar rendering, photorealistic avatar animations. We published this on the VRST, on the IEEE VR last year and the year before. And most of the times we were using these things to typical stuff that you all know, like, for example, first of all, we wanted to know how we can solve the technology behind it. Then what is the impact of these, let's say, more realistic looking avatars on oneself, and we also looked into how is the effect if you are in a social but only in a dyadic interaction, meaning just you and another of these avatars. In this work, we wanted to see, first of all, well, if we scale this up, I mean, social VR with just 2 people is social, of course, but if we really want to scale it, but think about this stuff in industry like a Pixel VR and all the others that now think about the internet of the future, where we all are embodied, maybe with large crowds in these environments. And ultimately, we are aiming here at a learning experience. We have a larger project where we want to have distributed immersive learning. And that also raised the second question: how does off-the-shelf technology scale with these requirements? Because we're going out of lab. This system is, at the end, will be used by our students, and the students will have all kinds of different maybe technological burdens at home, so we have to take care that these do not impair the overall quality of the system that we have. And then at the last, of course, how does these performance characteristics, which might be somehow changed by the underlying technology that we have here, impact the user experience? And also we are interested in, you guys might know it, and we're running this eeriness workshop for quite some time now, and I'm always saying that somehow the whole VR community have given up on the technology behind it. Most people are using Unity and Unreal. If I would ask you here, most of you would raise their hands. And we wanted to see, like, man, if we give up on that and we just use these off-the-shelf stuff, what can we expect from these systems after all if we really build these bigger systems? So here you have a view inside of the virtual environment. It's already some kind of learning environment where people are sitting around tables in groups in some kind of, let's say, teaching setup. There are different teaching setups. And you have to interact with your partners on the other side with a very simple drag and drop interaction task. So the task is not that important. It was more about you have to do something with your counterpart on the other side, but the other ones, I'll show you a video later, the other ones move as well. You can do this with all kinds of different approaches. Steed and Schroeder had a good taxonomy about how you could use and how you could model these avatars. You could start with puppeteered avatars. Think computer games. You have a game controller, you move the game controller, the avatar moves accordingly. This is not really controlled. I mean, you control the movements, but the movements are not in synchrony with your own movements, which makes a big difference. You can do reconstructed avatars, stuff that, for example, Bernd Fröhlich's group did, or it still does in Weimar, where you use a 3D depth camera and you not only capture the appearance and you also capture the movement in real time, but you also have to then transport the whole information at the same time, which is requires a high bandwidth first. And second, it's harder to change the appearance of the avatars. I mean, what you do is actually you're mimicking the real person. If we think about these applications like body ownership applications where you want to change the appearance of the avatars, it's getting a bit critical here. And you have the tracked ones that most of us know now, where we usually have some kind of full body tracking for our bodies, maybe with a reduced marker set and using inverse kinematics. What we did actually, we make a hybrid model where we reconstruct the avatars with photogrammetry, but then we track them with full body tracking or even with a reduced marker set. If you look at those, so this is just some pictures from the photogrammetry rig. If you look at the numbers below, that's just a sum. You don't have to read all that stuff. It's just, you can, I mean, if you know how many markers you have, then you know how much data you have to transport from the clients to the server, for example. Let's say we take line B3, which we were using, 6 times 6 degrees of freedom with a normal floating point encoding. You can just do the math and you end up, for example, if you say you want to scale up to 125 avatars, you scale up to 1.6 megabytes per second that you need just for the clients to transport this data. Still, then it has to be transported back to the client, so thinking about what kind of architecture you have, I will talk about that in a second, that these numbers will be increased drastically depending on what kind of infrastructure you are having. So the system that we have, it supports various avatar types. It's a client-server architecture, and we decided to go for the Unreal Engine. First of all, we have quite some knowledge on the Unreal Engine. Unity is not the best package if it comes to the networking part of things, so Unreal is much better in that case. And we wanted to have a real distribution scenario. So this is not artificial. We want a real distribution scenario with 125 computers connected, where all of these computers basically control one of these avatars. And then we want to benchmark, first of all, the performance, then the perception of the performance of users, and then finally the subjective experience of co-location and the scalability. You don't have to go into this architecture. I've said we don't have so much time, but you can look it up in our paper. So a little bit I have to say about the distribution architecture. We're following basically let's say the common knowledge how you do this in Unreal. That is, we have a client, the client sends the whole information from their avatar movements via a server-based RPC, which is remote procedure call, to a server. The server transforms the whole stuff in variables. It just controls the state. It has the authority over the overall simulation state. And finally, the server has to distribute all these information back to the client, meaning the clients in plural, depending on how many clients you have attached to it. Some of you guys who are more from the computer science part know that we have multicasting, but as we know, I've said we're going into the real world. Multicasting is good in labs, but multicasting on a DSL line connection somewhere on the world, that's basically not existing. Meaning the multicast has to be simulated by the server. So if you have 10 clients connected, the server basically has to send this data 10 times. Well, actually 9 times, because it doesn't have to send it back to the client. It just receives the data from. That would be useless, but that's just a fraction of the numbers that you really need. If you look at these numbers, you can easily calculate then, for example, what kind of out-client bandwidth you have, the in-server bandwidth that you have, if you have the number of clients, the fidelity in bytes, and the simulation rate, and then you can just make the math. You can do a prediction, basically. You can say, like, well, this is what I would expect with my fidelity. This is the bandwidth I would expect here to have. Our evaluation setup, like I said, was a real setup. As you can see here, we had 2 immersive clients on the upper row. They were all connected via a 2-layered switched backbone, and then we had all the other computers on the bottom, which did all the simulation, so a real setup here. So we're coming to the results, the benchmarking. So what happened here? First of all, we did latency measurements to see how the latency changes when we just increase the number of clients. And as you can see here, starting from 50, the latency increases. Specifically, if you look at the variance, which just does a jump. So for us, from the prediction here of the numbers, you can see that, okay, maybe 25. That's something which is much less than the numbers that we actually were calculating. You can do the same thing in the graphical analysis, then it looks like this. As you can see, again, 25 looks pretty okay. Then starting with 25, these numbers just go up. Again, if you do the math, you're way below the theoretical bandwidth of a gigabit connection, which is kind of surprising. Maybe it's not surprising. We can talk about that later. So about the network statistics also, just taking this again, 25 is the one I'm always choosing here. We have this in-rate, out-rate for client and for server. And if you do the math from the formulas I gave before, you have a prediction that says, like the prediction would say here, we have 6,900 kilobytes per second. Turns out when we measure it, it's just half of it. So something happened here between the prediction we had and the black box engine that we were using. They did something. Again, maybe we can talk about that later. There's a few ideas what's going on, but there is a drastic difference between what we were expecting and what actually we could measure. So there seems to be some kind of optimization going on. If we go for the performance perception, the same thing happens here. The performance is degrading. Now we ask people how they would rate the performance by watching videos about the interaction. And as you can see, there's the chances that this is just by chance are pretty low. We have high significant values here, and they all start roughly from the 25 level upwards to 125 when it gets completely unusable, asking for fluidity of the animations, the synchrony, and the annoyment. Then we did the subjective experience. We're measuring a mixed crowd with just avatars where some of them were looking realistic and other ones were looking completely artificial. And the within factor, we just did a randomization of the number of avatars to see how that scaling affects it. We didn't do it for the whole scale because we knew that with 25 we already have this limit, so we didn't went it for the whole scale. We said, like, we go up to 25 and then we choose just one which was way above that. We chose 100 to see if this really does what we want to do. Of course, we measured things like the immersive tendency questionnaire, the cyber sickness, and then we wanted to have some qualitative feedback. How does it feel to be in the virtual environment? What do you feel about the presence of the others? Do you think you could interact with these? So that's basically what we were interested in, right? How would people feel with such a crowd of avatars? So again, we did the whole thing in vitro, meaning we asked the people inside of the environment. We didn't put them out. They could do the rating on the different scales. Usually it was Likert scales here, and they could do the whole thing during the stimulus. We also had a few subscales for co-presence, impression of interaction possibility. We were asking for the uncanny valley, and we had some open questions, and then of course the SSQ at the end to see what's going on. I have to do a bit fast forward here because Rob already showed me the 5-minute sign. The whole thing looks like this. If you're inside of this environment, you can see it now from the first person view. You're interacting with somebody, you have the crowd around. You can see that they are animated, they do some typical animations. This is the video-based measurements that we were doing up front to see how people would interact the whole thing. The same thing then watched through the HMD and something of the in vitro rating for our questionnaires. And oh, 1 minute, no, okay, results, okay. So what are the results? That's good with the results. The results confirm the ones from the performance benchmarking and from the subjective perception. So we are in line between the technical things and our user studies. There are some effects, but I spare you the effects. They are in the paper. The co-presence increased for the number of avatars greater than 2, and the mixed crowd had an interaction effect. They amplified the whole thing. If we had a mixed crowd, realistic and non-realistic avatars. Again, statistics, I spare you. The increasing of the number of avatars just to the limit before, then detrimental effects occurred. Again, that was also statistically valid, as we can see here. And the 25 clients condition seemed to be the best one because it was just before everything went really bad, and it was just good enough to have enough avatars to create this co-presence. The uniformly human-looking crowd was less eerie, but also less attractive, which was interesting in the case. Again, that was also significant, and I spare you this again. This is all the qualitative feedback. I just summed this up. We were asking the users, and there is no really confirmative pattern to find. Some found it super cool, others were just like, well, everything is so unnatural, unreal. It wasn't really easy to find out from the qualitative statements what is actually going on here, so not conclusive, as I will tell you in a second. So, yeah. Our summary, how does it feel to be surrounded by virtual others? Well, I can tell you right now, it's inconclusive, at least from the questionnaires. We have good ideas. We have found interesting design implications. For example, maybe it's better to have a mixed crowd with different looking avatars because people felt, for example, that they had a higher chance of interaction. That's something we haven't expected at the beginning. How does the off-the-shelf technology scale with embodiment requirements? Well, unexpected. It hampered the prediction, and it really complicated the analysis. And we are quite experts when it comes to the Unreal Engine 4, but it's still a black box, although you have the source code, and I could rant for hours about that one. Basically, it says, like, we found something here, and there we couldn't control for it. If you think about it as an experimental setup, that's a bad message. We lost control of our really to-be controlled values here. So if we don't find anything here, it might as well be because our technology kind of failed at that part. And how do the performance characteristics impact the user experience? Significantly. Severe technical impact, and we have a lost control here. So there is something that all of you should keep in mind when you go for these off-the-shelf tools, which are now so handy and so easy to use. Specifically, if you're from other fields, be aware. That's something, there's a lot of confounds with technology involved nowadays, specifically with the ones that are basically done for computer games. So that's about it. Thank you. I'm only 1 minute over the time, I think. And that was the minute where I had to thank Rob, so I'm actually on time. That was your minute.
Please come to the microphone and identify yourself before asking your question. Again, that's time maybe for 2 questions.
Yeah, Jan-Philipp from Weimar University.
Hi, Bernd.
Thanks, Marc. Great to see that somebody still cares about the low-level problems. The thing is, the single server approach that you use doesn't seem right, right? Why do you have to have 120 people served by a single server? If you look at proxemics, you know, if you're out of the range of a certain subgroup of the people, you probably don't have to serve them by the same server, and the update rates for people further away, you know, can go down. So it might actually scale if you have a kind of a hierarchical approach, right?
Yeah, I mean, we're not that naive. That wasn't the goal. The goal was to see what can we do with the technology if we go for this very simple approach. And we are computer scientists, you are also. I mean, we have tons of ideas how to optimize and speed up the whole system, but we deliberately did not want to do this. We were thinking like, okay, if we just go by the blue book, like how does EPIC say how you do this? How would we end up here? Now, I mean, we want to use the system in a real scenario. So my students now are working on it and doing exactly this. So they're doing distributed server setup here. We do caching on the server side. So it's all going to be implemented here. But keep in mind, that takes a lot of knowledge on the computer science part. And the whole thing is that people are, I think, intrigued by the easiness of the interface of these tools nowadays. So it's all easy. We can just use it. And we were surprised, by the way, that the numbers we could measure were so far below what we have predicted. That's order of magnitudes lower. And that's something really, which is really strange. And if you look at what happened in the system, it really ended up that one core was 100% flooded. So there's an I/O-bound thing in the Unreal Engine going on, which we could explain, but that's a different topic. So it was desperately, and we are working on it now to change it. It was more like, okay, this is where we would end up with.
Okay. I'm just wondering if 125 will ever be necessary, or whenever you have that many people, you can always split it into smaller groups.
Yeah,
right?
sure.
That was the point.
You can always partition. That's true.
So I'm sorry, Pablo. I really have to call it. Sorry about that.
Next time.
Let's thank Marc again.